bad. Oh, is there? Is the audio coming in twice? Oh, I think now it should be better. My iPad was muted. Okay, I hope the echo is gone now. But I should still be able to hear you all. What was I trying to do? Right, I need to erase the stuff we haven't talked about. So today we will be continuing the material from yesterday, and I think we're in a pretty good position to comfortably get through all that I planned. So we don't need to rush or anything, but we should be able to finish week 2 with linear independence today. Actually, this should not be here. Are there any questions before we start? I mean, we have still 3 minutes before I'm allowed to officially start. Okay, mistake fixed. Yeah, this is where we left off, and then we'll go from there. Does anyone know by any chance if it's possible to sort the video participants to be shown first in Zoom? Something I was wondering about. I know that there's some of you with webcams on, but you're sometimes on different pages when I have to scroll through. Let me see. I can manually move them. Oh my. Yeah, I don't think I have the time to manually move. Maybe if I go to settings. Oh, yes, I can hide non-video participants. So I'm not going to be seeing any still images. Yeah, that looks pretty good. You might have noticed that the first recording you could see is 2 students next to my video feed. I realized that if I record to the cloud, this doesn't happen. So if you feel more comfortable turning your video on, then I can assure you now that there will not be any recording of you in the video. All right, it's 10 past, so I will I'll start with the lecture. And as I promised last time, because it was kind of rushed towards the end yesterday, I'll review this theorem that we ended with. So remember that I introduced what a span is, and I introduced linear combinations. That is what's in the span, that's the space or the set of all the linear combinations of a given family of vectors. And this theorem says that if every single vector that we're given here, v1 up to vk, is an element in V, then the span of these vectors will be a subspace. So it's not a surprise that the vectors will be contained in V, because by the vector space axiom, we know that the operations in V, when we combine two vectors, either by adding them or by scaling them first and then adding them, will never leave V. So we know that this is contained as a set. It can't be bigger than V. But then the important thing that we need to check is the subspace conditions. And well, we did this here. So I listed the two conditions that we need for theorem 1.28 to apply. And this just means it has to be non-empty, and the term alpha times V plus W has to be in the vector space and in the subset for two vectors and a scalar. So this is exactly what I've written here in this line. Notice that the vectors here in this case are linear combinations. So this theorem is very abstract in general, but this means we need to apply it to the case at hand. So in this case, the 1v from theorem 1.28 will look like a combination of vectors, and the w will also look like a combination of vectors, but it might be a different vector. So this means we might have different coefficients. The c is still the same, it's just a scalar number. So if you compute this, I first had to introduce what it means to add two linear combinations. And well, that was what I've discussed here on this bottom of this page. Well, we can actually infer from the axioms of a vector space that if you have two sums of vectors, two linear combinations, and you sum them together, you have a sum of sums, but that is just a sum by changing the parentheses. So what I've explained in the shorthand notation, I can also explain notation. So if you have one sum of many vectors, and then you add a different sum, say beta 1 v1 to beta k vk, might as well regroup them so that, well, first of all, we know that addition is associative. So it doesn't matter which sum of the many sums that we have, we do first. So we can delete these parentheses. And the next step is it is commutative, and the commutativity tells us that we are allowed to regroup them. So we have alpha 1 v1 plus beta 1 v1. So we can bring this vector, this term, all the way to the front, and likewise resort them in a way with the others, so that we have the alpha 1 and beta 1 together, and so on. Alpha k vk plus beta k vk. I should just move this up here. All right, so now that we have this, we can apply a next axiom of a vector space, which says that whenever we have a sum of a vector scaled by different scalars, which exactly happens here, then this will be equal to the sum of the scalars and then applied to v1 and so on. But now what we see is exactly that this looks just like a linear combination, but the coefficients are just the sum of the previous coefficients. So we added one coefficient to the other coefficient for each I. Yeah, that's the addition. And scalification of linear combinations works in a very similar fashion. Any questions about this notation? Excellent. I can actually see people nodding their head, or like that's helpful. All right. So now that we know how the operations work for combinations, we can actually check if this sum of two vectors with one scale is still in the vector space, the subset. But this just means it has to be a combination, again, the linear combination. So if we start here, then we first apply the scalar multiplication, and we see, well, this is just another combination where the coefficients are each scaled. And then if we add them, what we do is we add the ith coefficient to the ith coefficient of the second term. And then we see, well, the condition, there's always this this condition that tells me whether an element in the vector space is also an element in subset. There's like a pruning condition. And in this case, it's very simple. It just means, well, it has to be a linear combination of these vectors, v1 to vk. But this is just the form of such a combination. And by that argument, it's just a matter of perspective. We're done showing that this is in span S. And now that we've shown this second part and the first part that it is non-empty, we're done showing that it is a subspace by theorem 1.28. Any questions about this proof? Yes, Quinion.
I have a question about, are we allowed to use all the theorems we have proved in our class in the assignments or tests?
Yes, absolutely.
So we don't need to prove them again during the assignments like that?
No, except for like in a special case when the problem statement of the question becomes trivial if you use the theorem, then it kind of makes sense that you can't use the theorem. Like say if the question says, prove this again, or like do something similar. But in general, you can build on what we do here. So that's the purpose, that we build machinery and you are equipped with all these theorems that you're able to solve questions.
Okay, I see. Thanks.
Any other questions? Daniel?
Yeah, just to build off that last question, should we refer to the theorems we proved in the class? Like, for example, I know we proved the theorem, well, it was called the property in the notes where you had -1 times a vector equals the negative of that vector. How would we like refer to any theorem that we proved in class? Should we just say,
yeah, if it's a minor, if it's a minor proposition, you can just say we've shown in the lecture that this is true. Okay. Anything that's major, and we're gonna only get to the major parts. So for example, where was it? One. So like this, for example, what we just proved, it's not, I mean, everyone who's working in algebra, who's going to be grading the tests or whatever, they all know that this is true. And if you tell them this if you just say it is a theorem, everyone knows what you mean. And if you want to be very careful, for example, by the with the subspace condition, or it's not in this week, you can just state like maybe it has a name. The most important theorems have a name anyways.
All right. Thank you very much.
Okay, so before we continue, I'll give you a discussion. I'll give you, I think, 4 minutes or so. And I want you to discuss this. I mean, discuss means in this case, just think about this for yourself. If R and S are two families in a vector space, then what can you say about these 3 points? So if the one family is contained in the others, so say this is a bigger family of vectors and every vector in here in R is also in S, is it true that the span of R is also contained in the span of S? The next one is, what if you take the union of these? So you just take a bigger family and you put everything in this new family that was in R or in S. Is this span equal to the span of R plus the span of S? And lastly, is it true that R is always in the span that it spans? So I'll give you 4 minutes and then we'll discuss this together. And if you have questions, you're welcome to write in the chat. I'll just answer there so that no one gets distracted. All right. Let's start with number 1. Can someone tell me what they think about it? Oliver.
So I was thinking I could show this using the example. So for example, if S is the span of R3, then we know that the XY plane is a subset of R3, which is R2, and therefore this means it shows that the span and the span of R2 is E1 and E2, which is contained in span S.
Yes, very good. So it's always good to start with an example. But if you prove something in general, we have to do one more little step. I mean, this is completely correct. But there's one little step that we can do to make this more abstract. So in this case, you're right that if we have this, then you argue, well, this is going to be if we take the span of this, then we're going to have R3, which is just the 3 space. And if we have this, then we take the span, then what we're going to get is just a plane. And we can see that this just sits in this span and in this of 3 by this as this plane, this XY plane. So let's try together to use this and make this more abstract. So basically, can someone tell me what is too concrete about this? Oh yes, someone noticed that that I mixed these two, but that's fine. I just said that S is the one containing R and not the other way around. Thank you. You could just tell this to everyone. Like, you don't have to message me privately. It's I stand by my mistakes. Okay, so one thing that's too specific here is that it's 2 and 3 elements. I mean, not every set containing another set has 2 and 3 elements. So what we need to do is how do I write this? Well, more abstractly, what we do now is we just say, well, what if R doesn't have just 2 elements, but we just call them V1 to Vk. So now there's any number of elements is allowed. And then S will look like it will have to contain R. So we have to have these first K elements, but then the list might go on. So this is a K plus 1. And this is just a label. So Vk could be anything. It just means that we sort them and we say, well, the first K might as well be the ones also in R. Okay, and so what does it mean to be contained as a subspace when we have, or as a set, we want to show that span R is in span S? Well, if you show that every element in span R is also in span S. So we just pick a generic element in span R. And this looks like some linear combination of the V1 to Vk. I don't know why I'm talking here. This should be a discussion with everyone. So how can I proceed? Can someone help me? Yeah. Sorry, is it a T? Aditya?
Yeah. So the way I did it was I expanded this, and then in order to make it have the same amount of vectors as a linear combination of an element in S would, I used a property that when you multiply a vector by 0, that will give you the 0 vector, which means when you add that to that linear combination, it remains unchanged, but it now becomes a linear combination of all the elements instead of S, and therefore belongs in it.
Yes, exactly. Thank you. So what we do here is exactly what I've mentioned now a few times. that the perspective is often the solution. You don't have to do much in terms of math. You just have to view it in the right way. And that's a matter of practice. So don't worry if this if this idea or this change of perspective seems counterintuitive, because you just get used to it. So now what we have here is that, well, we might just write this maybe with betas. But now the j, the index, has to go from the first element in S to an element to k plus m. So this means what we've done, we've added more vectors, but they don't contribute if you choose the coefficients to be 0, starting at k plus 1. So beta j is equal to 0 for j greater or equal than k plus 1. But now this is this here is a generic element in the span of R, and we've shown that it's also contained in the span of S. So this proves that span of R is in the span of S. All right, so I think we need to do 3 slides per hour so that we get through them with the middle. And this is slide 3. What about the others? Yeah, let's do, where do we put this? Let me just add a page before. And then just make a note that we continue up there. So 2 and 3 will be on this slide, the page before. Okay, so for 2, any ideas? We want to show that the span of R union S, and I just don't mean the real numbers, just R, is equal to the span of R plus the span of S. Adrian.
Yeah, I think we can just use double containment again. So you can
Okay.
start out with like a vector in R union S, and then just write it as a linear combination of vectors in R and S. And then basically just show that that way you show that if you assign 0 coefficients, then basically this would also be again a subset of, I think, R and S. So you like basically one way first, and then after you assign the 0 coefficients, and you can show the other way. If that kind of makes sense.
Oh yes, okay, I understand. Yes.
Yeah.
I was thinking something different, but let's just do it that way. So you can show that if you let me think.
So
No, I think this. If so, what about an element? So we have to also a generic element doesn't necessarily have 0 coefficients for half of the set. So
yeah, I think that would be my second step. So I guess you should start with just any random vector V element of span of R union S.
Yeah, let's do that. So let's start with I equals 1, and let's go to k plus m with alpha a vi, and here R is the set from v1 to vk. Notice that R are different than in 1, and here we just have k plus 1 to vk plus m. So now they do not have any intersection. They may, but let's just say they don't. And then what we can do is we can just split the sum, because now what we have is we have a sum of alpha 1 v1 alpha k vk. And we can insert these parentheses that, remember in the previous proof of the theorem, we just use a similar argument to remove the these parentheses. Now we can just add them. And then what we notice is that Now this will be a linear combination in span R. And this will be in span S. So this means for any linear combination in the span of R union S, we can decompose them exactly in two elements, one in span R and one in span S. So this shows the first containment, that the left-hand side is in the right-hand side. And I just denote this by, so if we want equality, we need to show first that the left-hand side is in the right-hand side, and also vice versa. So this one is done. Okay, secondly, well, this is kind of just the other one backwards. So let me just to be just to give you these details, you can just copy this. So now we start with with an arbitrary element in the sum of these two vector spaces, these subspaces, and then, well, we just go backwards. So this is the sum of just all alpha I vi from I equals 1 to k plus m. And then this is, of course, an element in span R union S. Oliver.
So the span of from I equals 1 to k plus 1 m is the conclusion we brought from question 1, right? When
no, this is something completely new. So we don't use we don't use the discussion 1 here, because in this case we had as k, we wanted that that S contains some subfamily R, and then we want to show, well, if we span, this containment is still true. And here what we want to show is that if we have different families with no intersection, just different families, and we take the union of these, then this, and we span, we get the sum of the spaces. Okay, let's just talk about, without writing down, what 3 means. Is it true or is not true that that a family of X is also in the span of this family? Well, I might as well write it down. So it is true, and the reason is, so if R is V1 to Vk, then of course for any Vi in R, 0 times V1, 1 times Vi, 0 Vk is in the span. So if every coefficient for the ith is 0, I mean, we just get back this one vector, and then this is its linear combination in span R. So this means that R itself, just the single vectors, the discrete set of vectors, is in the subspace. Okay, any questions? Adrian and Daniel, you have your hands up. Is that on purpose or?
Oh, sorry, it was just from.
And then Quinn Yuan, you have a question?
Oh yeah, I have a quick question about the first one. How can we just conclude that, conclude directly from the last step to that span R is a subset of span S? How do we just conclude that from the sum of beta j Vj?
Because, so notice that I start with a sum that goes from 1 to k. So yeah, it's like these don't exist. So that's the thing that we have. Yes. And then we allow to add zeros. So adding zeros doesn't change the vector. Yes. But then this is the same as adding vectors multiplied by 0. And now if we do this, I mean, you might wonder what's the point? Well, the point is now this is a sum. This is a combination of all the vectors from v1 to vk plus m. And this is exactly the vectors in the bigger set.
Oh, I
So
see.
now by defining the betas, I mean, I should have probably written two things here so that beta j is equal to alpha j for 1 lesser equal than j lesser equal than k, and beta is 0. So we just call beta every coefficient here, and we just say, well, at a certain point they're 0, and before we wanted them to be in the previous combination.
Oh, I see. Just like
Okay.
the following coefficients are 0, and this becomes the elements of span S. So that is why span R is
exactly.
Thanks.
Yeah, thanks for asking. Claire?
Could you please explain question 3 again? I'm still a little bit confused about that.
Oh, okay. I think maybe I went too quick because I think this is the easiest one of the three.
Okay.
It just means that, so if you have a single vector, is there a way to write it as a linear combination of all the vectors? Well, same trick as just now. We just add the other vectors, but we multiply them by 0. So what we so the vi is the sum of all the v of all the vk's, the vj's, but then everything but this one vector is 0. So there's k vectors in the sum, but we just want to keep the 1. So we just multiply everything with 0, and just one coefficient is non-zero.
Oh, okay. Thank you.
All right. Let's go to a corollary. So this corollary, a corollary just means after you've proven a theorem, a corollary is like an easy step to get a little bit more. So it kind of is a direct implication from the theorem. And the theorem that we just proven is that the span of a family is a subspace. Now, the corollary that I want to show is that that if we have two families which are not necessarily equal, so notice that here R has the V's in it, and S has W's in it. So they might be completely different. But still, there's a condition under which span R is equal to span S. And this exactly is the case if R is contained in span S and S in span R. So this means if we have S and R, there's no relation between them. But then if we apply span to both of them, then this one is contained in here, and this one is contained in here. Then they're equal, they're the spans. But the sets might not be equal. Okay, this might seem confusing, but let's just get this corollary and in how this follows from the theorem, and then we'll see an example where this happens. So don't worry if this is confusing. We'll see a very concrete example in a second. So why is that? Well, if R is contained in span S, then we are in this situation of, what was the theorem called? 134, where we have a family where R is a family of vectors in a vector space. Span S. So again, the key here is the perspective. We're now viewing span S as a vector space because every subspace is a vector space, and we just saw that span S is a subspace of V. And then we see, well, if we have this, now theorem 134 applies to this, and then you just have to literally translate every letter to letter. It says that span R is a subspace of span S. So just to emphasize how we applied the theorem. So this is the family in the theorem, and this is the vector space. In the theorem. And then it says that the span of the family is a subspace in the vector space. But in this case, in this particular case, it just means that span R is a subspace of span S. And then if we apply this again, to S, a subset or S, let me use the same wording. Family in span R implies that span S is equal to span R. So far we only have this containment, but then together span S is equal to the span R. It's kind of a new proof. So anyways, I think details are helpful, I hope. Any questions about this? All right, so let's go to the discussion. Well, this is basically just the steps from before, the corollary applied to a special case. So we have two families. The first one is S, as written here. And the second one is the familiar one of the monomials, 1 to the power x to the 3. And so first of all, I want you to show that every single vector in this family of monomials is in S. And then use the corollary to conclude that span S is the same as P3R. Remember that this is just the span of 1 x squared x to the 3. So we know this from before. I'll give you 3 minutes. I think that should be enough, and we're running a bit short on time again. If you have questions, just write in the chat, and I'll monitor the chat. All right. Let's see what you came up with. And I want to say again that, and maybe I didn't say this before, if you just have a vague idea, that's completely fine to tell me about it, because even if it's just an idea and it's wrong, you're not certain about it, it's fine to add to the discussion. It only helps me to identify what questions you have, and then we can discuss about it this together. I think I've already shown in the first lecture that it's okay to say something wrong. So what about the first point? Idris, or Idris? How do you pronounce it?
It's Idris.
Okay.
I just had like a idea that this span, like a 1x, no, that's not a span, but like 1x, x squared, and x cubed. Like if you, in S, if you factor out like some x, like for like the second element, like you can factor out an x. So you have an x term multiplied by something else, like 1 minus 2x, and then like for the second one you can factor out, like the third element actually, you can factor out like an x squared and like the, wait, does that work?
Yeah.
Or something like that. I just had a vague idea.
So you want to find some coefficients the right way that everything cancels, but only one x is left over.
Yeah.
Yeah, that's correct. So okay, for the first one, can I just write for all 1x, x squared, x to the 3? Well, the first one is simple. This is just 1 times 1. So where this is the coefficient, this is the vector. For the second one, as we just heard, well, what we can do is we can start with this vector. So we have 1 times x minus 2x squared. But then we have too much. We don't want the 2x squared. But then we note as well the third one has the same element, the same monomial, so we can just subtract it. So we just subtract 1 times 2x squared, but this comes at a cost, the cost of adding again 3x to the 3. Okay, we can also deal with that by just adding the right amount of the last one. And in this case, well, we need to make sure that we kill this 5. This is done by dividing by 5, but then we also need to multiply by 3. So this will be in total a coefficient of 3 over 5. And then we have 5x to the 3. And I basically just built this exactly so that it is equal to x. And this is how you find coefficients. And this is a linear combination. So it is totally obvious that this is a linear combination of vectors in, did I call this S? Yes, in S. So this means this is in span S. Okay, can someone else continue? Jency, you have your hand up.
Yeah, so do I continue from x squared?
Yes.
Okay, I got 1/4, 1 plus 4x squared, minus 1/4 times 1.
So what was the factor?
1 plus 4x squared. The second last term.
Oh, yes, 1 plus 4x squared. And then?
Minus 1/4 times 1.
Yes, perfect, thank you. Again, we have coefficients, and they're chosen in exactly the right way so that if we combine the vectors that we're allowed to use, then this will be in the span of S. So it's kind of a game. I only allow you to use these vectors, and I ask you to find the right coefficient so that they give me x squared. Okay, let's see. Someone else for the next one? Sam?
Yeah, so, well, it's just going to be 1/5 of the 5x cubed.
Yeah, okay.
Everything else is 0.
Yeah, right. So we just need one term, and whenever I just write one term, as you just mentioned, everything else is 0. I don't even bother writing the zeros anymore, because if there's zeros, then it just doesn't matter. But technically, if you wanted to have every vector in linear combination, we would have to add the zeros. Okay, so this is 1. This was the first part. That's completed. And now the second part. So now comes again the different part of solving this, where it's not math, but it's just a perspective that we need to understand. So why is this? Why does 1 help us to say that the span of S is equal to P3 of R? Oliver.
Is it because it allows us to use theorem 1.3.4, and that says any vector space V in a family of vectors such that will result in a span of S belonging to the family? Meaning that S, since S is part of span S, S is also in P3R. You can conclude that they're equal.
Yes, I'm not sure if I understood the first part correctly, but the last part was definitely correct. So we have two things at this point. So observe, and this is what you said last. Every element in S is a polynomial. So all vectors in S are polynomials. So S is a family in P3 of R, but I think we all agree that if we describe P3 of R as the span of all the monomials, it's the most convenient way, because the coefficients of the linear combinations are exactly the coefficients of the polynomial. So we know that S is in this span. But now the second part, from 1, we also have, what do we have from 1? Yeah, it's exactly the problem statement. It says that every monomial, so maybe let's call this R. That R is contained in the span of S. I don't want to write all the terms. In words, every monomial 1 to x to the 3 is in span S. And now we have exactly the situation as this corollary states. So it says that if we have two different families, in this case the monomials and these other polynomials, which are just made up, and we know that one family is in the span of the other family, and the other family is in the span of the first family. So observe that this is exactly this cross diagram. So we have both containments. Then we know, and we've just actually proven this corollary just now, then we know that the spans of them are equal. So this means the span of S, let me start with S is the span of R. And this is by design. This is by design exactly the polynomials of at most degree 3. Okay. Any questions? Jency, you have your hand still up. Is that a question?
Oh, sorry, it's from before.
Okay. Okay, so it is now 8 p.m. So I do want to take a break in a moment, but before this, does it make sense to start with this now? Yeah, let me just briefly for 2 minutes say something about the prelude here, and then we'll take a break so that this can maybe sink in, or you can like just stare at this while you take a break. Okay, so now that we know, and this is exactly what we did just now, that a vector space can have different spans. So the upshot of this discussion here was that V, a vector space, and then we say it can be spanned by the set, can be spanned by many different sets or families. And as an example, I've written 2 different spans that are both equal to R2. And you can convince yourself that this is actually true. So if I write them down, this is the first. Let me write this here. So the first one just looks like these 2 standard vectors, which is 1, 0. No, this is not 1, 0. This is 1, 0. And this is 0, 1. And we usually call them E1 and E2. The second span, however, contains different vectors. It contains 1, 1, minus 1, 1, and 2, 0. I'm assuming that here is this is the axis, the coordinate axis. So this is R2, and here as well. This is R2. So the question is if they both do the job of spanning R2, how do they differ? Or do they even differ? Is there any meaningful difference between them? Okay, and I'll answer this after the break. Let's take 5 minutes until 8 past 8. I didn't resume the recording after the break, so we've missed now about half an hour of recording. I mean, the notes, I'll still share the notes as always, but yeah, the recording will not contain this bit about the discussion. I hope that there was nothing too confusing that you want to rewatch. Quinn Yuan, you have a question?
Oh yeah, I just want to ask, why should we say the largest index X by?
Yeah, that's just convenience, because if there was something non-zero after this point, then I would have to write, I have to write this here as well, and then I would basically just say this is a combination where I just pick out one element, but the others continue. It just, I mean, it doesn't really matter. You can choose this to be true, but it doesn't have to be true.
Oh, okay, sure, thanks.
Andrew?
I just want to confirm again for the discussion section above, is the verdict possible or impossible?
No, it is possible. So, yes, we can find such a combination.
Okay, thank you.
Okay, and there's one more part of this theorem that we want to prove. It is that the span doesn't change. Now, luckily, we have a very powerful corollary, if you remember. So this corollary is exactly coming to play right now. Did I give this a name? I don't think so. But I think it was the corollary of theorem 134, if I'm not mistaken. Well, let me put this towards the bottom, and let me start with just with an observation that if we have V1 up to Vj minus 1, and then Vj, well, let me use the same notation. So we exclude the Vj, but we only delete the Vj from this list. And this is contained in, well, first of all the V's, because if you delete one V, you don't get anything more. And then this is in the span of V1 to Vk. So we have one family in a span. And then likewise, also because of part 1, Vj is in the span of V1 where the j is left out. So this also holds the whole first part, that if we delete delete the jth element, actually we don't need those because they assume to be 0. Then the Vj is still in the span. That's what the first part says, and we've already proven that just now. So in particular, because this is true, all the V1 up to Vk are in the span of V1, Vj excluded, Vk. And now we have two families which are contained in each other's span, just as in the corollary. So by the corollary of theorem 134, the span of V1, where the j is left out, is equal to the span of the original span where the Vj is still included. And that's the end of the theorem. That's all we wanted to show. Are there any questions? Okay, let's see what we still have to do in this lecture. So I want to go to an example, different theorem, and a true or false. Okay, I definitely want to do the theorems. This one is faster. Yeah, I think we have time for the example. So in 20 minutes, we should be able to cover this. Okay, so what I mean by the above example, that this theorem, oh, actually, I didn't call this a lemma, applies to the example in the prelude. And this just means that in the family, 1, 0, no, sorry, it was minus 1, it was 1, 1, minus 1, 1, and 2, 0. We can remove the third vector. Let's just call this V3, 2, 0. And two things are true. the two assertions of the theorem I'm gonna check right now. First, V3 is in the span of the remaining. So we have 1, 1, minus 1, 1. And then technically I want to write 2, 0 removed. So that you understand why I write this, so where it comes from. And I mean, it is in this case quick to verify that indeed if we subtract from 1, 1, so we have 1 times 1, 1, minus 1 times minus 1, 1, we get 2, 0. So this is exactly, this is a combination, a linear combination in the span 1, 1, minus 1, 1. And second, well, as we have seen, R2, okay, this is not exactly the example, but R2 can be spanned by 1, 1. You can verify this if you want. I should write this R2 in the middle. So this is R2, but it doesn't hurt to include more vectors. I guess the crucial part is that even though we remove one from the family, the spanning set, the resulting span doesn't change. And if you look at the picture above, I can just draw it again. If you have this vector available and this vector, and then also this vector, you don't need this vector. You can still travel to any point by a linear combination of these two if you scale them and add them together. Any questions? Okay, so now that we are able to have, now that we have this theorem about reducing a dependent set, I mean, you can just guess what's next. It's extending an independent set that it's in the way that it stays independent. So now we have something that is independent, but it's not big enough to span the vector space that the vectors live in. So this means we have V1 to Vk, an independent family, and it doesn't span V. Then two things are true. Well, the first one is kind of obvious. There's some vector not in the span. Otherwise, it just would be V. And the second one is we can add this vector to the family, and it remains independent. That's the useful fact here. So let me just quickly go over the proof. Well, this is, as I said, the first part. This is clear because if the span, I mean, the span is a V1 to Vk is always a subspace. But if span V1 to Vk is not equal to V, there is one element V in V such that V is not in the span. Okay, so what about the second part? So this is exactly the V that we want to add. So try to set 0 equal to alpha 1 V1 plus alpha k Vk. plus say alpha times v. So now we have the original combination of the original vectors, and then we have an additional vector in the combination. So now there are two cases we need to consider to prove this. And the first one is case 1, where alpha is equal to 0. No, sorry, non-zero. So if alpha is non-zero, same trick as before, we can divide by alpha. So what happens then is that that 0, I mean, 1 over alpha doesn't change to 0, is equal to alpha 1 over alpha v1 plus alpha k over alpha vk plus v. And then, just as before, these entire terms we can just subtract on the other side. And then we have that v is equal to minus alpha 1 over alpha v1 and so on. Does someone notice something fishy going on? Is there something that shouldn't be true? I mean, not in my proof, just in the steps that we take. I hope that's the only thing that's where something's wrong. Well, what is this? What is this right-hand side? No, this is not 0. I just I said the whole thing has to be 0, not the first part. What I mean is that this is a linear combination. Of v1 to vk. So in particular, this is an element in the span. But we said v is not in the span. We chose v in a manner that is not in the span. So yes, Jordan said it's a contradiction. So this is in the span of the v's. This is a contradiction. Can't happen. Or this is, yeah, let me just say contradiction. So this means we are in case in case 2, which is alpha has to be 0. Okay, so in the second case, try to keep everything on the screen while still being able to write. So now alpha 1 v1 plus alpha k vk plus 0 times v, because we just said it can't be non-zero, only has the trivial solution alpha, because the last term doesn't contribute. And so this has to be the trivial solution, because we know that v1 to vk is by assumption independent. So this only has the trivial solution, alpha 1 equals to 0, equals alpha 2, and so on, equals to alpha k, they're all 0. Exactly because v1 to vk are assumed to be independent. And so now in total, we've shown first that the alpha is 0, and then in one batch that every other coefficient is 0. But this means that alpha 1, alpha 2, alpha k, and alpha have to be 0. And if we go back to this this equation that we started out with, this was a test whether the new set with the additional vector v is independent. So we can conclude that v1 to vk with the additional v is independent. And this is the end of the proof. So we've just picked a vector in such a manner outside the span that we can add it and it's not destroying the independence condition. Are there questions? Mallory.
Hi, I sort of missed a little bit how we know that we picked V so that it wasn't an element of the span. That was just something that was given, or that was just one.
Almost. We just assume that the span isn't all of V. So this means if this is V, then the span is slightly smaller. So there's at least one element or a few elements which are not in the span.
Right.
And so if you pick that one, then the proof works. Of course, and now you can see, you can kind of stress test this proof. What happens if the span is already all of the vector space V? Well, in that case, our technique breaks down, and for a good reason, because you can't add anything without making it dependent. So there's a reason why we need to assume this.
Okay, that makes sense. Thank you.
Okay. Any further questions? Time is getting short. Kun Yuan.
I have a small question about the symbol, the second line, but span way to k. That part, the following symbol means that it is a this span, this set is a part of. I see.
It means that it's properly contained. That's something I explained last week.
Yeah, that's not. It cannot be the V, right? I see. Thanks.
It cannot be all of it, exactly. Okay, so now I have to choose between theorem or true or false. Which one would you prefer? Just write it in the chat. True or false or theorem. I mean, we have to do one or the other now, and the other one we can do next week. Theorem, that's surprising. Unanimously, everyone wants a theorem. Wow. Okay, so I'll go through the theorem. I mean, you can also look at these after the lecture, and I can just give away the answers at the beginning of next week. So there's no harm. Yeah, my brain is tired too. I'll try to go slow in the last 5 minutes. And this is not a hard theorem, I think. This is not terribly difficult. But it's very interesting because it kind of sums up what we started with in this lecture. So what does it say? If we have a family of vectors, and it doesn't have to be the whole vector space that it spans, but then this set of vectors is independent if every vector in the span has a unique linear combination. So this means if V is in the span of V1 to Vk, technically you could assume that you just find one combination. So this means that V is equal to some alpha 1 V1 alpha k Vk. But the question is, are those alphas the only ones? Is this the only combination or the only coefficients possible to produce V? I mean, that is a valid question, I guess. Exactly. So Andrew jumped the gun and went right to the intuition, which is good because intuition always helps you to prove something. So yeah, I'll draw a picture at the end in 5 minutes. So let's just do one direction for now. Suppose that v1 to vk is independent. And we assume for to get to a contradiction, we assume that there are two different ways. To write v in the span of this. Well, the first one is v is equal to alpha. I don't know why I'm using shorthand notation. I mean, introduce it for a reason, I guess, but kind of sticking to this. Alpha k vk. But let's also assume that beta 1 v1 all the way up to beta k vk is also v. And now we want to check, maybe they are different, maybe they have to be the same, and that's actually what I'm aiming for. So then what happens if I subtract the one v from the other v? I mean, the v's are the same. So this means 0 is equal to v, and in this case, we use this representation. And then we subtract v. And in that case, I want to use the other one. So I want to use this representation. So this means I get alpha 1 v1 all the way up to alpha k vk. And then I have minus beta 1 v1 minus all the other terms beta k to vk. All right. Now again, we can reorder the summons because we have commutativity condition. This means we have alpha 1 minus b1. And I'm also using the associative, now the other distributive property already. So we can group these terms together. And we have alpha k minus bk vk. And now magically, we arrived at an expression that tests whether v1 to vk are independent. So notice if you look at only the last equation, then this is the test whether the v's are independent. Let me delete. Let's do this later. I don't need the space right now. But by assumption, v1 to vk are independent. So the only combination that is equal to 0 has to be the trivial one. And the coefficients just happen to be the terms alpha 1 minus beta 1, alpha 2 minus beta 2, and so on. But now this is equivalent with alpha 1 equals beta 1, alpha 2 equals beta 2, all the way up to alpha k equals beta k. So this means we're able to show that if we assume, and technically proof only starts here, if we assume that the set is independent, we're able to show that every element in the span has a unique combination. If there are two ways to write it, then the coefficients are the same. So it is technically the same combination. Okay, well, I wrote here if and only if, and the only if condition is exactly backwards. If you go the same logic backwards, then you can prove the opposite direction. So let me just say, technically, the opposite direction would have to be done as well. I'm just going to omit it here because it's basically the same idea backwards. And I want to spend 1 more minute on the intuition. So now it's time to get some intuition. Okay, I think Andrew was the one who said this. But let's try to draw. Maybe with these. Now let's just draw 2 combinations of some vectors. So say the first one and the vector want to go to, if this is the coordinate plane R2, say we want to go to this point. And if there are 2 combinations, then this means we can use maybe this vector, and this vector. I just made these up, so there's no way to. This is only an intuitive picture. There's no math. I mean, math is involved, but no numbers. And now if there was another combination, say we go, I don't know, down first, and then we go here, and then we go here, then Andrew noticed that if we go the one combination forward and the other one backwards, so if we invert these, we switch back to green. So if we then continue the green path, but we go the pink one backwards, then we have a loop. So two different combinations for one vector implies non-trivial loop. And this, as we said in the beginning, implies
Professor, I think your screen froze.
Oh no. Okay, I mean, it's anyways time. I don't know, can I quickly solve this? Am I still in the meeting?
Yes, I can still see it, but it's not updating.
Okay, my iPad doesn't seem like Zoom doesn't respond anymore. So I have to go back into Zoom. Okay, let me end the lecture here. Let me just say that from this picture, you can see that if you have 2 different paths, you can go one forward to the other one backwards, and that will be a loop. The lecture notes that I'll upload, there will be a bit more explanation, and so you can look at this again to maybe understand this better. Okay, that's it for today. You're welcome to all look at these true or false questions. And I'm just going to go over the true or false questions at the end. No, at the beginning of next week. All right. Any questions at the end? I'll give you a week to think about the true or false. So I'll not include the true or false answers today, but maybe next week, so that you have a week to wonder. Okay, so in case someone has a question, I can reload the screen, the page if you want. Yeah, I can go over the last theorem next week again. Maybe remind me if I forget.